finish what I said about rules of unity and then have this kind of application about construction of ruler of compass, so which is more fun part. What?
It's a bit strange to relate a geometry problem with a field problem. So
that's actually and sometimes not at all true. So I mean the thing is. Algebra is something one understands, and very often you have problems in geometry, topology, whatever, and you want to understand them in terms of algebra. Next semester you will have a course in algebraic topology, where you kind of can understand, study problems of topology in terms of algebra, and your algebraic geometry is also something like that. Somehow the point is that mathematics is united, is one thing, and you always want to be able to use methods from one field in all other fields. So that's what makes things powerful. If you anyway, but I mean this is a bit different here because we have kind of a problem of elementary geometry, and so okay. So we're talking about roots of unity. So we had introduced this Euler phi function, which is a number of k between 0 and n, such that k is relatively prime to n. We'll see in a moment what this has to do with roots of unity. And we had noticed that p of n is equal to the number of n of units in Cn. And okay. And we had a formula for what this number is, but we will not repeat this now. And now we want to talk about, relate this to roots of unity. So, definition. So, let K be a splitting field of x to the n minus 1 over q, and that theta be a primitive nth root of unity in K. So we could take e to the 2 pi I divided by n. So we denote the set of all nth roots of unity in K by n. Nth roots of unity in K, so all the elements whose nth power is 1, and this is the set of nth roots of unity, and P of the n, the set of primitive nth roots of unity. Clearly, this is contained in this. And so I want to summarize some easy facts about this. So we have theta, we assume that theta is the primitive nth root of unity in K. So first we have that if I take this, the nth of unity with a multiplication, this is a group. So, in fact, so if it's clear, no? If theta and sigma are roots of nth roots of unity, then it follows that theta sigma also is. Not just take the nth power of the product as opposed to the nth power. Then, secondly, I can have a map from Zn, remember that's just short for Z mod NZ, to the nth roots of unity, which sends the class of a number k to theta to the k is an isomorphism of groups. Because clearly, that just says that if theta to the k plus L is equal to the theta to the k plus theta to the L, so that makes it what? Times obviously, times theta to the L, that's what I meant obviously, and so this would give you a homomorphism from Z to the N, and the kernel obviously is the multiples of N. Then, so a power theta to the L is a primitive nth root of unity if and only if the numbers, the greatest common divisor of L and N is 1, so L and N are relatively prime. Because clearly theta to the L times K is equal to 1 if and only N divides L times K. So if now this L is relatively prime to N, then the number actually has to be a multiple of N. And then fourth, so this is also so if I have a divisor of N, so I only look at positive divisors, and we have ED, so the nth roots of unity are contained in the nth roots of unity. No, because if theta to the if eta to the d is equal, if eta to the d is equal to 1 and d divides n, then if I take to the power n, I also get 1. And more precisely, we can write that the nth root of unity is the disjoint union over all divisors of n of the primitive d roots of unity. Now, this is essentially also by definition. So, if you have a primitive d roots of unity and d divides n, obviously it's an nth root of unity. And if you have an nth root of unity, it will be a primitive d root of unity for some d. The smallest power, so that you get 1. And this d must be a divisor of n. Okay. And then we have number 5. The number n can be written as the sum over all divisors of n. Again, just positive integers which divide n of p of d. This is the consequence of this, because n is the number of nth root of unity, and phi of d is the number of primitive d roots of unity. So if this is the disjoint union of these sets is the n, then the number of elements n must be equal to the sum of the number of elements here. Okay, so this is an easy remark. Okay, so this just collects some facts. And now we want to consider we want to consider the minimal polynomial of primitive and root of unity. And so we still look at the splitting field of K splitting field of x to the n minus 1 q. And so let theta 1 until theta phi of n be the primitive nth roots of unity. We know there are precisely as many, because we see that the primitive nth root of unity can be written as theta to the L, where L is a number smaller or equal to n, which is prime to n. And so this is, according to our definition of phi of n, the number of those is precisely this. Okay, so this. So then the nth cyclotomic polynomial is just the product of x minus these. So I write a large phi of n, which is x minus psi 1 times and so on x minus psi 2 until x minus psi phi of n. So a priori, this is just an element in Kx. We later see that it's actually defined over Q. So from what we have written here in this remark, we have some easy corollaries. First, we know that the degree of Pn, that's basically the definition, is equal to the Euler phi function. And the second remark is more interesting, namely, the first write it down, if I take x to the n minus 1, this can be written as a product over all divisors of n of phi d of x. If I want anything with of phi. So why is that? Because we use this identity here. So phi d is the product over x minus ci, where the ci run through this set. And so the disjoint union of these sets correspond to the product of these things. So essentially, this formula directly by definition gives us that. Because obviously, if I take the product over e to the n, take the product over all roots of unity, x minus this root of unity, this gives x to the n minus 1. Okay, so this is an important corollary, because if you think of it a moment, this tells us that we can kind of turn this around. We can use this to compute all of them by recursion. So let me see. So use this to compute the phi n recursively. How is it? So, for a given n, so we do it by some kind of induction. Obviously, know what phi 1 is. No? Phi 1 is equal to x minus 1. No? The definition. No, the first. So, now, if we have, so assume up to a certain n, we know all of them. We know all smaller ones. So we know if we want to compute it if we want to compute phi n, so n divides n, so phi n is one of these. So we can, it's just, so therefore we can just take this expression, can take this and divide it through all other ones. So we get that phi n is equal to x to the n minus 1 divided by the product over all d divides n, and d is bigger than 0, set of phi d of x. No? Just bring this on the other side. What? Well, if it's a divisor, it must be less than n, no?
When we take phi n,
What?
when we express phi n, we should.
Yeah, you're right. So d must be less than n, obviously. Yeah, okay. D, I obviously forgot this point, otherwise the recursion, yeah. Okay, so 0 smaller d smaller than n. Okay, obviously that was, I missed that. So that means, so I would, inductively I would know all of them, and then I just divide this by this, and this is this polynomial. So we have a very simple way of computing all of them. So here we are supposed to write down this thing, and we don't know what these things precisely are, but here we have a simple way of computing them, and you can also easily see that you can compute. So as I said, P1 is equal to 1, then P2 is equal to x squared minus 1 divided by P1, so was not 1, x minus 1 divided by x minus 1, which is x plus 1, then P3 is equal to, so the divisor is also only 1, so x to the third minus 1 divided by x minus 1, which is x squared plus x plus 1, and just one further one, P4 is x to the 4 minus 1 divided by P1 and P2, so divided by x minus 1 times x plus 1, which is x squared plus 1, and so on. So it's a very simple thing. And as a corollary to this, you get something which is maybe, if not so obvious from the definition, namely phi n of x is a polynomial with coefficients in Q. Because obviously this one is phi 1. So again, we do this by induction. So x to the n minus 1 is a polynomial with coefficients in Q. Phi 1 is 1. So assume all the other ones are polynomials with coefficients in Q. So if we do division one by the other, the coefficients also has coefficients in Q. In fact, if we are a little bit more careful, you can see that these polynomials are monic with integer coefficients. And if you do division with rest of monic polynomials with integer coefficients, you get monic polynomials with integer coefficients. So with a bit more care, you actually show that phi n of x is monic in set of x for all x. Okay, but that's okay. So that's just the fact. So you see this. So this is kind of useful because it gives you something which you can't see so easily otherwise. And now I come to the theorem about this, which unfortunately one part of it I cannot prove. So maybe I can do it here. So we want to know, well, so we take k as before this. So I don't actually need it. So theorem. So we take, so z is a positive integer, k is a splitting field of x to the n minus 1 over q. And so then the first statement is that this polynomial Pn, this cyclotomic polynomial, is irreducible. In Qx. Okay, I should maybe say, so this is actually quite difficult to prove. So I don't think, I mean, maybe with a big effort I might be able to prove it if I use a whole lecture. I mean, to prove this statement. This is the most difficult part. It just is, somehow a difficult fact. I mean, you have to use that somehow this monic with coefficient in zx, and then maybe reduce modulo some primes and do this and that. So there are some complicated arguments, and eventually, after big effort, one proves it. We don't have the time to do it, so I don't. Okay. Second statement is that if I take the degree of the splitting field over Q, this is again our favorite Euler-Phi function. And the third one is we know the Galois group of K over Q, which is just the units in Z, not nz. So the Galois group of K over Q is Z, not nz. No, I wrote exactly Zn. Done. If you want isomorphic. Okay, so this is the statement. So here we have a, what's the case where we have some interesting abelian Galois group for this extension. So one we don't prove. We assume it for the rest. So then 2 becomes obvious, no? Because we have that theta is a primitive nth root of unity in K, then it follows that K is just equal to Q of theta. Because obviously, if you have a primitive nth root of unity, then this polynomial splits, and this is actually 0 of it, so it has to be contained in the splitting. Okay. So, and now as this polynomial here, phi n is irreducible, therefore is the minimal polynomial. Of this thing of theta over Q. So it's the degree of the field extension, therefore, is equal to the degree of the polynomial. Okay, now we come to the third part. So we want to define a group homomorphism from this Galois group to Z n star. So how do we do this? So, I mean, it's somehow the usual thing. We have that phi n is a polynomial with coefficients in Q. So therefore, as we have seen many times before, the elements in the Galois group have to map zeros of this polynomial to zeros of this polynomial. So as the zeros are the primitive roots of unity, it means the Galois groups map primitive roots of unity, primitive nth roots of unity to primitive nth root of unity. Okay. and then the element in the gyro group will be determined by what it does to our theta here. So as Pn is in Qx, by this eigenvalue used many times, we have that elements sigma in the gyro group of A over Q map zeros of Pn to zeros of the n. That means primitive nth root of unity. So primitive nth root of unity. Okay. So on the other hand, every member sigma in the gyro group is determined by what it does on theta. So that means if I have two elements in the gyro group which map this theta to the same element, then they must be equal. And this is just because K is equal to Q theta. So if something, the elements in the gyro group have the identity on Q, and they have two elements which do the same thing to theta, then they do the same thing to everything, because every element here is a polynomial in theta with coefficients in Q. Okay, so that's, we just have to see what happens here. So we have sigma of our theta will be some primitive nth of root of unity, so we can write it as theta to the k with greatest common divisor of k and n equal to 1. No? The k is an integer. So now we define a homomorphism. From the gyro group of k over q to z n star by sending the map which sends so sigma with sigma of theta is equal to theta to the k. We send this to k plus n c. Isn't that what n? So the class of k. So I claim this is this power is precisely well defined up to n. So this is a well-defined map. So theta to the theta to the k, where if I take theta to the k plus n is equal to theta to the k, and precisely that. So these two of these powers are equal if and only if this is equal. And I claim it's a group homomorphism, and this is also clear if so this is well defined, and it is a group homomorphism because so it's a homomorphism because if I take if tau of theta is equal to theta to the L, and sigma of theta is equal to theta to the k, then well, not into the room, then it follows what is it? If I take, say, tau of sigma of theta, this is tau of theta to the, which one was it? To the k. This means now we have to replace theta by theta to the L, so this is theta to the k times L. So we see that the composition of these elements corresponds to the path product in Zn star. So it's a group complex. And obviously it is injective. So I don't know, maybe I call this thing theta. So theta is injective because there is no, because if so what does it mean? An element in the Galois group. So how do you get mapped to 0? I just say because if sigma of theta is equal to theta, this is equivalent to sigma equal to the identity. And this is equivalent to, that this number n here is 0. So the map is, okay, so the map is injective, there's no kernel. Because again, k is q of theta, so something is identical in q, and on theta is identical. Okay, so we have an injective group homomorphism from this Galois group to Z mod n, to the units, yeah? But we know that the number of elements here is phi of n, the number of elements is also phi of n, so it's an isomorphism. This, no, that one is an isomorphism. So we have described the Galois group in this case. No, we have an injective map from one to the other, and they both have the same number of elements. So it's nice. Okay, so this was as much as I wanted to say about the story with the roots of unity. Now I will want to some extent apply this for these constructions with ruler and compass, which is I mean, it's more for fun, but I hope it is fun. It's a very classical problem. So this is constructions with ruler and compass. So we'll only be able to sketch this. I cannot give you all the details. That would take a little bit longer, but I can at least roughly explain. So these are, this was the way, this is the way of doing geometry in the Greek school, like with Platon and whatever. So it was studied by the Greek school. Of Platon, around 2,500 years ago. I mean that was started there. I think one can find some complete. And so the question is, what figures in the plane can be constructed with ruler and compass. So we have to explain later in precise fashion what that even means. Somehow, one does, and at least we also did this in school a little bit. So, I mean, there a number of the one question. There are some classical questions. One was called the Dingle Problem, just as an example. So can one make an edge such that the square of the edge, the length of the edge is if you make a cube with that length, with the length of the edge, you get 2. So in other words, can we construct third root of 2? This was somehow one of the things that Greeks worried about, and they didn't succeed. And anyway, another one: can one trisect an arbitrary angle? So if you already know how to make a certain angle, is there a construction which gives you a third of that? I have to explain later what. And then another question which we are mostly will be concerned with is which regular n-gon can be constructed. That's the most interesting of these problems. First, I have to tell you what all this means. So what do I mean by construction with ruler and compass? And I will, at the same time, I also algebraize the problem. So we identify the plane with the complex numbers. No, just r plus ir. So identify. So these are always identify the plane R2 with C R plus I R. And we look at the following constructions. So first I need some notation. So if I have 2 points, I want to look at the line from them. So for points P, Q, which are different, in C denote PQ, the line which goes to P and Q. I mean, you can, obviously you learn in school or something, like if you're given the coordinates of these points, you can write down the equation of this line, but I'm not going to do it now. So secondly, if I'm given, say, a point P and C, which I always use as 2, and some positive number, so obviously then it has to be a real number, to denote K, P, P rho. Maybe it's not so great at P and rho, but anyway, KP rho, the circle with radius rho around P. So we have P, we have this circle, and this length here is rho. Where I should have maybe have said by the length, well, okay, no, we know. So also maybe just if P is a point in C, I also want to write P to be the complex absolute value, so the length of this point is a vector. So if I write P equal to A plus IB, this is square root of A squared plus B squared. So limit. And now we have the following elementary construction steps to, which one means by construction with ruler and compass. I talked about the points which are constructible with ruler and compass, which are all that I can obtain from just the points 0 and 1 by certain elementary steps. So the set M subset C of points constructible by ruler and compass is defined recursively as follows. So, first we start by just saying that the points 0 and 1 are supposed to be constructed. So this is the 0th step, what we start with. 0 and 1 are in M, so just these 2 points. The first step is, if I have 2 lines, which I can define using points I already have, then also the intersection will lie there. So if P is different from P1 is different from Q1, and P2 is different from Q2, are elements in M with the line P1, Q1, puzzled, okay, is different from the line P2, Q2, then it follows that the intersection of these 2 lines, P1, Q1, intersected P2, Q2, which will be actually a point, is also lies in M. Then, second one is we can intersect with a circle. So we can intersect a line with a circle, where the radius of the circle is allowed to be the distance of any points that we already know. Okay, so you put so that means, so if we have points P1, Q1, P2, P1, Q1, and P2, Q2 are all points in M, and I assume that P1 is different from Q1, so that we can make a line through it, then if I take the line from between P1 and Q1 and I intersect it with the circle with around this point P, with radius, the difference, the length of the distance between these two, then this might be 0 points, it might be 2 points, it might be 1 point, but anyway, all these points are then in M. No? So the picture is you have here, you have this line, so P1 and Q1, you have a point P, and you make a circle around it, and then now you get these 2 new points. And somehow this was not very much, the thing is done in such a way, the radius of the circle is supposed to be the distance between these 2 points. You can put them in there. So in this way we get more points, and the third one is that we can also intersect 2 circles. So again, if you have 2 different points, and we have P1, Q1, 2 points, and P2, Q2 in M, then we can look at the intersection of the circle around P with radius, the distance between these 2 points, with the one around Q, with the distance between those. So that is, the radius we always have has to come from something we have constructed before, but then it must be around points we have. So we just have here 2 points, and we have a circle of the radius we somehow already know as a distance of 2 points, and then we get these new points in addition. And so these are all the steps that are allowed. We're not allowed to do anything else. Okay? So a point is constructible by ruler and compass if we can obtain it from just these 2 points by applying successively as often as we want any of these steps. You can write this outside more so explicitly to make sure. So explicitly we have that our set M is the subset of C of all Z or Z and C such that there exists a chain. We have 0, 1 is contained, is say our M0 contained in M1 and so on until Mn with Z being in the last one, such that at each step you get from one to the next by applying one of these 3 steps. So and Mi plus 1 is obtained from Mi by applying one of the steps. 1, 2, 3 for to appropriate points. No? If you want to apply 1, we need to choose 4 points of the previous one and then apply it. If you want to apply 2, we have to choose 5 points. If you want to apply the third one, we have to choose 6 points, and then we apply to that and we get them next. Okay. So now this is by itself right. So now we have to somehow try to make this a bit more algebraic. So until now, so we have the following statement, which I cannot completely prove, but can sketch at least some parts of it. Namely, what is not obvious from the definition is that M is indeed a field. It's an extension of Q, and we have the following theorem. So 1. M is a subfield of C which contains Q. Okay, so this is the important thing. The second one is that if I have an element B which is so if I have a complex number B such that its square is in M, then it follows B is in M. So it's a subfield in M which together with every element also contains its square root. And the third one is maybe easier. So if I have point B in M, then it follows the complex conjugate is also in M. Okay, so this is the first thing one can show here. Now, as you can imagine, there's a lot of work. You actually you have to, so what does it mean? So to prove 1, we have to show if A and B are elements in M, then it follows that A plus B, A times B, whatever, minus A, 1 over A, are also all elements in M. And obviously what this means is you have to make a construction which out of 2 elements makes their sum or their product or whatever. You can imagine these are, and you have to do this for all these things, and something like the product of 1 over A is quite complicated. But I can at least sketch 2 of them. Maybe I sketch this for A plus B and minus A, because there you can easily think of a drawing. Because, how can you, what can you say about A plus B? The distance of A plus B from A is the length of B. And the distance of A plus B from B is the length of A. So that means we have that A plus B is an element in the circle around A of radius B intersected the circle of radius around B of radius A. I mean, I can also try to make a drawing. So if here is 0, then maybe this one. So I make it as vectors because that's how but anyway, it's this point. This is A, this is B, and this would be A plus B, and obviously, well, essentially, and then so you take a radius like B around this will be something like this, and you make this thing of radius A around this, and somehow, I don't know, and it will somehow intersect there. Okay. Now, I made, normally it would be 2 intersection points. Now, I didn't make a good drawing, but I mean, it's just this obvious fact. The other one is even simpler. What is minus A? You can take the point 0. Here you have A. If you take the line to 0 and A, and you make a circle which goes to 0 and A around this, the other intersection point is minus A. So that means minus A is, whatever. Minus A is the only element, so you obtain this. This is, you take the radius, you take the line, 0A, intersected with a circle of radius around 0 of radius the length of A, and this thing will actually consist precisely of minus A and A. And so we obtain minus A there. So these are, and multiplication is obviously more difficult, and this might be even more effort, but you can, one can do it. It's not incredibly complicated. And for the second one, I will only very roughly, I will only do some part of it.
Which one didn't you?
What?
We haven't proved.
Oh, well, no, but that's, if you have a subfield of C, it's a field of characteristic 0. And so and every such field must contain Q. No, it contains, if you have a field if you have a field in C which contains 0 and 1, then it contains all fractions. No, there's nothing. So this is a kind of tautological. But so maybe I will not say much about 2. So we have to, so one has to construct the square root of a rational, construct square root. And I haven't really of some complex number, so if A, if I write it in polar coordinates, I can write it as r times e to the 2 pi I some angle. So if I get that the square root of A is equal to square root of r times e to the 2 pi, so maybe pi I r, right? So one has to do, therefore, so where this r and phi are real numbers. No? So therefore, there are two things one has to do. One has to be able to make the square root of a real number and to halve an angle. And half an angle. So, it's not very difficult to make the square root of a real number. You have to do something with, for instance, you could do something with the Hate theorem of, somehow, it has somehow thing to do with Pythagoras, obviously.
Each real?
What?
For each real? Whatever?
I mean, if you are given a real number,
Yes.
then you can construct its square root.
Okay.
Okay? So, and this is, obviously it has something to do with the theorem of Pythagoras or something like that, or with the Hate theorem in triangles. So somehow you use that, and you will get this. And I will just talk about the angle, which is easier, if I have it. So I just say, so what do we have? So assume we have here's 1, here's 0. So I mean, to construct an angle is the same as saying to construct this number, e to the 2 pi I phi. No, that's what I mean, right? So assume this is whatever. This is e to the 2 pi I phi. So what does one do? So I mean, maybe I can make a drawing. So we make let me see. So make a circle around this point. So we have, so anyway, we have this line and this line, which is we make a circle around this point through the origin of the radius 1. Well, if it's round, it would be better. And I make also the same circle here. Now it's even less round. And then you can see from the precision of the drawing that the angle here is precisely half the angle. So this thing, this point here is e to the pi I. So very simple, it just intersects these two. Okay, so you can construct the half angle always. As I said, okay, so this would then give this. So as I said, I don't talk about this. And this with the complex conjugate, I mean, somehow it's not difficult to construct. If you're given a point A in the complex numbers, this is the real axis. It's not difficult to construct a line which is orthogonal to a given line through through a given point. It's a standard construction one learns in school anyway, we'll not repeat it. So we can therefore make this line. You can figure out how it goes, and then obviously we just take the circle with radius a around this, and this will be a bar. This is the real axis. Okay, so with every element it contains the complex conjugate. Okay. So now, so anyway, this I sketched at least with a little. I mean, it's just a sketch. Obviously, it takes maybe an hour or something to do it properly. In particular, the addition, the multiplication, and so on. There's many details. to make all the drawings. But there's nothing very deep going on. You have to understand some elementary geometry to understand how to make these things, and maybe. But at least these few things one can see easily, and for the other ones, it's just a bit harder work. So now we want to so there's a more precise state. I mean, I just wiped out the theorem. Anyway, I have another theorem which is maybe a slightly more precise statement. So the following are equivalent. So first, the point C in C, so is an M. And the second one is we have a certain chain of intermediate fields, so that it lies in the last one. So there's a chain. Q is equal to L0 contained in L1 and M in C, such that this element C is in L. But that's would say nothing, but one more condition, and we have that the degree of the field extension Li over Li minus 1 is always equal to 2 for all I. I mean, how can you see this? For one thing, we have seen here, it's written here, if something is in M, then also its square root is in M. So this is a degree 2 extension. So this will, if you do it carefully, give you one direction here. So that, if you have an extension of degree 2, and then it always is given by extracting a square root of an element, because we know that if we have a field extension with a cyclic Galois group, in this case the Galois group is V2, and we have all necessary roots of unity, which in this case is minus 1, then it's given by that. But anyway, it's elementary. You can just write down the formula. So this gives you one direction. For the other one, you have to see that whenever you make such an elementary construction step, the new element either lies in the same field as you were before, or in an extension of degree 2. And so you can somehow imagine if you're given these points and these points, and they live in a certain field, then the intersection point will live in the same field. So intersection of lines lets you stay in the same field. You don't have a field extension. If you can work it out with coordinates, but anyway, it's easy to see. You have to solve some linear equations. If you have a line given by 2 points, and you have a circle, circle gets less and less round, but anyway, you have a circle where I just put where you are given the radius and this. You can, by doing in coordinates, you can actually see that these intersection points will lie in an extension of degree 2 if all the points we were given to make this construction were lying in a certain field, then these 2 points lie in an extension of the field of degree at most 2. And the same is true if you are intersecting 2 lines. They also lie in an extension of degree at most 2. And so this gives you the other direction. I mean, it's something one has to work out. You have to write down the coordinates, you see it. I mean, it takes some computation, but it's easy. Okay, so this is this theorem. And now we can already. Let me see which page it is. Where's my page? Okay, so expector over I don't really. Yeah, I think it's okay. I don't know why I didn't say this corollary, but we have an obvious corollary. So, namely the following. So let Z in M. So let Z be an element in M. No? Then, if I look at the degree of the field extension Q of Z over Q, this must be a power of 2. And why is that? Well, in some sense it's obvious. So we have this chain here. So assume we have Z is an Mn where we have a chain Q Lm, and the degree of Li over Li minus 1 is equal to 2 for all I. So then it obviously follows that the degree of Lm over Q will be equal to will be power of 2, namely just it will be equal to 2 to the n. And now Q of Z is an intermediate field of this extension. Of this extension Lm over Q, because it's Q of Z obviously is contained in Lm because Z is in Lm. And so, therefore, the degree of the field extension Qz over Q must divide this number. And so it's also power of 2. So that's the degree of Q of Z over Q divides Q to the n. Thus is the power of 2. Okay. And so with this we already can see that 2 of these 3 problems are not solvable. I mean, cannot be, things cannot be constructed. For instance, so the corollary is, so this was this Delian problem. Square root, so the third root of 2 is not constructible. And this is clearly because the degree of Q, third root of 2 over Q, is equal to 3, which is not the power of 2. Okay, so it's very simple. Once one sets up the whole thing, it becomes dead. And in the same way, so not every, also the trisection of a general angle is impossible. So for that it's enough to give you one angle which is constructible, which one cannot trisect. No, one doesn't have to talk about general constructions. I can give you one angle which I cannot trisect. And this is very simple. So proof it's enough to show that what is it? E to the 2 pi I divided by 3 cannot be trisected. Okay, so this angle So just this. This angle here. And obviously this thing can be done because everybody knows how to make an equivalent. You know if you have a circle and here you have 1, you can take a circle of radius 1 around this point, of the same radius, we make this, and this point is this will be e to the pi I divided by 3. And so obviously you can either do it twice to get this, or you know anyway that you can multiply things, and so you get by multiplying this twice you get this one. Okay, so this one can be so this thing can be constructed, but I claim it cannot be trisected. So we have to show that e to the 2 pi I divided by 9 is not an n. Okay, and so that's quite simple because we know what its minimal polynomial is. It's a primitive 9th root of unity. No? So we have, so this is e to the pi I, 2 pi I divided by 9 is a primitive 9th root of unity. So we know its minimal polynomial is P9, and it has degree phi of 9, no? The Euler function applied to 9, and it's easy to compute from the definition that this number is equal to 6. And so that's not the power of 2, and so therefore this cannot be constructed. Okay, and then finally we come to the most interesting problem, which is the one that Gauss considered, which is the construction of regular n-gons. So I should maybe say to construct a regular n-gon, it's enough to construct e to the 2 pi I divided by n. Then you kind of, and by constructing the n-gon, I mean you construct its vertices. No? Okay. So regular n-gon. So to construct a regular n-gon, it is enough to construct e to the 2 pi I divided by n. So as we see here, this has been known classically, even also to the Greeks, so classical constructions for, I think, n equal 3, 4, 5, and 6. And we have just seen it's impossible for n equal to 9. So sometimes one can do it, sometimes one can't. We have to see what is true. And so Gauss constructed a regular 17 gon when he was 19. As I said, this was somehow what decided him to become a mathematician, and he considered it important enough that he required in his will that this would be scratched into his gravestone. A regular 17 gon. So he really was proud of that. And so now let me state, and he proved something better, namely precisely which regular n-gons can be constructed. This is one example, and this has to do with some little fact of number theory, which is Fermat primes and numbers. So let me briefly introduce this. So for a positive integer, n, so I call fn, which is 2 to the 2 to the n plus 1. So that means first make 2 to the n, and then you take 2 to this power. So if n gets large, this goes very, very fast, and be the nth number. So they were looked at by Fermat, and he you can look at them. So it actually doesn't actually necessarily have to be positive. I think it's also possible if, so it could also be n equal to 0. So we have f0 is equal to 3, f1 is equal to 5, f2 is equal to 17. So it seems to have something to do with these numbers here, and so on. F4, these are all prime numbers. And Fermat conjecture, on the basis of this rather scarce evidence, that all Fn are prime. And I mean this. What?
It's still a conjecture?
No. It's as true as it can possibly be, as false as it can possibly be, as far as we know. So Euler showed that F5 is not prime, and these numbers have been studied also with computers for a long time, and they have kind of looked at very many of them up to very high n. And until now, no other prime number has been found. So it seems so one doesn't know. No, it might be there's some very huge ones, but it is possible that these are the only prime numbers. So, which would mean that in some sense, as Fermat knew this, that his conjecture would be as false as it possibly can be. Because if you start with some data, obviously that. Okay. So now for us, so if, however, Fn is prime, we call it a Fermat prime. So as I said, we do not know whether there are more Fermat primes than these 5, but for all we know, there could still be infinitely many. No? They just could be very, very far away. So, okay. And this plays a role for us because of the following. So, if I take an odd prime number, such that if I take p minus 1, that this is the power of 2. So it's 2 to the k plus 1, the prime number. Then it follows that this power itself must also be power of 2. So then p is a Fermat prime. So if one insists that if I subtract 1 from the prime number, it is a power of 2, then it has to be of this crazy form. It must be kind of a double power of 2. So this is actually quite the simple fact, kind of elementary, namely, so we write this p equal to 2 to the m plus 1. And we have to show that this itself is a power of 2. So assume, if it's not, it contains an odd prime factor, an odd factor. So if m is not power of 2, then n is divisible by an odd number n. No? And so we can write, therefore, m equal to q times L, where L is okay. Let me just see that I have the same. So maybe I want to say, I take maybe my odd number is q. So, and then it's where L is some positive integer. And then we can ask ourselves, then I just claim that then this cannot be a prime, because one can easily write down how it factors. So then, according to us, P is equal to 2 to the q times L plus 1. But you have this kind of geometric series, no? You have this thing. So if there would be a minus, you would always write how to pull out a factor. If there's a plus, it depends on the parity of what you have here. But you can do it. But in this case, if this is odd, it precisely works. And so this is 2 to the L plus 1 times 2 to the L times q minus 1 plus minus 2 to the L times q minus 2 plus and so on, and it ends with 2 to the L. So minus 2 to the L plus 1. If you just multiply it out, you get this. And so it's not prime. So okay, so in some sense, to say that something is Fermat prime precisely means that it's that p minus 1 is a power of 2. And now we are in a position to state the theorem of Gauss. Which is so we take so that n be some positive integer. Yeah. So the following are equivalent. So first, the regular n-born is constructible. The second one is, if I take the Euler phi function of n, this is the power of 2. And the third one is that I can precisely say how these numbers can be done in terms of Fermat primes. So there exists a pairwise distinct Fermat primes. What is it? Say P1 to PR. So we have R different Fermat primes. So if this is maximally wrong, this could be at most 4. Then such that this number n can be written as and some element, some number m, some non-negative integer m, such that n can be written as 2 to the m times the product of these Fermat primes. Okay. So that's an interesting, I mean, it's a kind of non-trivial statement, no? You know, it's a little bit, in some sense, we still don't have the complete answer because for all we know there might be infinitely many Fermat primes. So but at least modulo this thing, we know precisely what this can be. Okay, so let me sketch some of the proof. It's actually not very you will have to remember what I just wiped out. So I have done. Okay, so let's look at the proof. I will not give a complete proof, but I will give some of the ideas. So all these three things are supposed to be equivalent. So let's go from 1 to 2. So if we have a regular n-gon, then phi of n should be power of 2. That's almost trivial, no? So, because by what we said before. So let theta be a primitive, for instance, just theta be e to the 2 pi I divided by n. Then it follows by the theorem, then we know that if I take q theta over q, the degree of this field extension is phi of n. And we have a theorem that if the element theta is constructible, then this degree must be a power of 2. We have the q theta over q must be a power of 2. Okay, so this is simple. I mean, after all the effort we did. Now I want to show that 2 and 3 are equivalent. So let's take a number n written somehow as a product of primes. So now I also call them p1, pr, but they are just prime numbers. No? So p1 times so p1 to the L1 times PR to the LR. So every number can be factored uniquely as a product of powers of primes. So it's the prime composition of n. So this Li some positive integers and the pi are primes. So then we have to see what's the condition for phi of n to be a power of 2. But we have a formula for phi of n. So we had shown the following formula. Which is maybe slightly different from what I write it down in a slightly different way from what I wrote down before, but it's equivalence that phi of n in this case can be written as p1 to the L minus 1, L1 minus 1 times pr to the Lr minus 1 times p1 minus 1 times pr minus 1. What I actually wrote, it was p1 to the L minus p1 to the L1 minus 1 and so on, but it's the same formula. So we know this formula. And this has to be power of 2. So when can this be a power of 2? It just has to look at it. So we know, so it means that everything here must be a power of 2. Okay? So we know this, a prime number minus 1 can be power of 2 only if we have a Fermat prime. So, or obviously, I mean, maybe I should have said, obviously, if p1, if this is equal to 2, we also get 1, which is also okay. So first, we have, so we see that P1 to PR must be 2 or Fermat primes to satisfy this condition here. And then this thing also has to be power of 2. But these are powers of this prime number P. So they can only be a power of 2 if P is equal to 2, or if the power is 1. I mean, if the power Li is equal to 1, which means this power here is 0. So, and Li is equal to 1 unless Pi is equal to 2. So that means, and on the other hand, if we do have that, if we have 2 to the something times the product of Fermat primes, then obviously we will get a power of 2. And so this gives us this condition, and this is obviously an equivalence. This thing will be power of 2 if and only if we can write this in this form. Okay, and then so the last part would be to show that this one that let's say 2 implies 1, which then actually allows us to, so 2 implies 1 means that, which in some sense then means we actually do have a construction, which is maybe so, and this follows from the following theorem. Namely, so we know that if we have, if we add, well, I first just state here. So let Z in C be algebraic over Q. So let F be the meaningless polynomial of Z over Q. And we look at the splitting field of this meaningless polynomial. So let K over Q be the splitting field of F over Q. So if, it's actually if and only if, but we only need one direction, if the power K over Q, if the degree of the splitting field is a power of 2, then Z is constructed. So that's some kind of partial converse to what we had before, that if something is constructible, then the degree of Q, that element over Q, must be power 2. Here, to have that actually it is constructible, we must have that the degree of the splitting field is power of 2, which is a more difficult condition. Obviously, the degree of QZ over Q is a divisor of this. So if this is a power of 2, then also the other holds, but this is a stronger condition. And okay, and I mean that it follows from this theorem is kind of clear. So maybe I can first sketch the proof of this. I mean, not really sketch. So we use a theorem about groups. Namely, the following. So if G is a group of order, say, p to the n for prime p, then G is solvable. And furthermore, we can make a normal chain that the successive quotients have all order p. So, the way around. Gn contained in Gn minus 1 to 0 equal G such that G I divided by Gi plus 1 is equal to P. I mean the order, the index for all R. Okay. So in our particular case, so the Galois group here, so thus in our case, the Galois group of F, which is the Galois group of K over Q, has order, so I call this G, has order 2 to the m. So therefore it is solvable. So thus the theorem applies. And we can use the fundamental theorem of Galois theory to get a chain of fields. So by fundamental theorem of Galois theory, there exists a chain of fields which correspond to it. So this Gn is maybe just the identity, no? So the fields which was it K contains, so K equals Kn contains Kn minus 1 and so on, K0 equals Q, such that the degree of Ki over Ki plus 1, Ki minus 1, is always equal to 2 for all R. And so therefore it means it is constructive. So therefore we know, so under this assumption, this precise is and we have nz is in Kn. So by the theorem that we have, it means Z is constructive. And notice that this, I now wiped it out, that this applies to the construction with ruler and compass, because if I take Q e to the 2 pi I divided by n, this is the splitting field of the minimal polynomial. If I take, this our polynomial, so Q, again, e to the 2 pi I divided by n is the splitting field. Of Pn, which is the minimal polynomial. Of the same element. No, because we know if we have a primitive root of unity in our field, it splits, and the splitting field is that. So therefore, the stronger assumption is true here, and so we can apply it. So I wanted to have one kind of funny, nice application of this. Maybe a little bit fast, but you can see how this thing is made. Anyway, so thank you.